All right, this is just, you should go through and copy all these notes first. They are also on Edline, but this is just hopefully will be a short video to kind of just go over what we talked about in class. You should go through the other video though, just going over the example of the hypothesis test first. So you should watch this one second for day one. The hypothesis testing, it's not just for your science class. We can also do it in stats. We have statistical hypotheses, which are testing something about our population, and they may or may not be true. It's just a standard procedure for testing a claim. Okay, the hypothesis test uses sample data to make a decision about whether or not to reject the null hypothesis. So I can make certain claims, and then based on what those claims are, I can write out these statements with stat terms. When you do a hypothesis test, you have two hypotheses. You have your H naught, this is a 0 here, which is the statistical hypothesis that states the value of the population parameter, such as p, mu, sigma, or sigma squared, and we're only going to deal with p and mu, is equal to some value. So then this is called the null. It'll always contain the condition of equality. And it is the one that is assumed to be true until we can decide to reject it or fail to reject. The alternative, these are the possible symbols. Your book uses this H1. That states a specific difference between a population parameter and specific value. So this one will always contain the condition of inequality. So it'll always be not equal to or less than or greater than. So when you're doing a problem, don't worry so much about what the person is claiming to decide where it should go, but worry more about what is the symbol that you have. You can have two types of hypothesis tests. You can have a one-sided test or a two-sided test. The way you decide is by looking at your alternatives, so your H1. So if I had the null that said greater than or equal to, so mu is greater than or equal to some number, or p is greater than or equal to some number, my alternative would say less than. And I would look at my bell-shaped curve, and I would be finding a probability or an area in the left tail. My arrow points to the left. My tail is over here on the left. I could have the null being less than or equal to and the alternative being greater than, and then I have this area shaded, and that is the probability that I am finding. So these are both one-tailed tests because you're only interested in one area. We could also have two-sided tests where our null is equal to and our alternative is not equal to, and then we would be finding the probability in two tails because we don't have a direction. So this was just practice writing the hypotheses test. So this first example, as an example, they believe that the birth weights are going to increase. The current is 8.6. So I say that the average is greater than 8.6. There's no equal sign there, so I would put that in my alternative. Whereas the null would be the opposite of that, so I have to include all the other possibilities, so it would be less than or equal to, and this is a one-sided one. Conditions. We're going to check conditions just like we did last chapter. They'll be very similar, and I'm just going to go over those in detail when I go through the specific tests. Your test statistic or your test value, it's computed from sample data. It's used to make the decision as to whether or not you should reject the null. The test statistic tells you how far away the sample value is from the population parameter. The test statistic is found by converting the sample statistic to a standard score, such as a z-score or a t-value, and then I'm not worrying about the chi-squared. I'm not going to teach it in this chapter. It'll come up in a later chapter. The general form of the test statistic is going to be the statistic minus the parameter divided by the standard deviation of the statistic. So we're going to have three things just like we did last chapter. So we have proportion. So we have z is equal to p hat minus p over the square root of p times q divided by n. I know last chapter we used p hat and q hat in the denominator. In this chapter we're using p and q because we don't, in this chapter we actually believe we know what the population proportion is equal to. In last chapter we were trying to estimate it. Mean, so we'll either have z, we'll have x bar minus mu over sigma divided by the square root of n, or we'll be using t, and we'll have x bar minus mu over s divided by the square root of n. Once we calculate the test statistic, we can use it to determine the probability of getting your sample results if the null is true. So now we need to discuss p-values. P-values are the probability computed assuming that H naught is true. that the observed outcome would take a value as extreme or more extreme than that actually observed is called the p-value of the test. The smaller the p-value is, the stronger the evidence against H0 provided by the data. So it's just the probability. It's like with the normal CDF or command or TCDF command. You're finding the probability of getting that value or something more extreme. You can easily find the p-value by using the standard normal or the t-distribution. If the p-value is very small, that means the probability of getting sample data, such as the data obtained, is very small, and it is evidence to reject the null hypothesis. So if you have a small probability, that means that the likelihood of that result occurring is very unlikely. So therefore, since it's so unlikely to happen, you would reject your null. If your p-value is very large, the probability of getting the sample data, such as the data obtained, is very large, and there's not enough evidence to reject the null hypothesis. You can have, so your probabilities, just like previously, can be anywhere between 0 and 1, and you need to sometimes decide, well, how much am I willing to tolerate? So if I got a p-value of 9%, is that enough for me to say that that's very small or very large? So sometimes in those gray areas, a statistician might decide in advance that they're only willing to tolerate a certain level. So we were introduced to the level of significance last chapter with confidence intervals. It's symbolized by alpha, and it's a complement of the confidence level. Sometimes statisticians want to compare the p-value to a fixed value. The statistician is deciding in advance how much evidence against H0 he or she will insist on. So it's called the significance level, and this is similar to using 0.05 as a cutoff to decide if something is unusual. The most frequently used significant levels are alpha of 0.01, alpha of 0.05, and alpha of 0.1. So this relates to like a confidence level of 99%. This is 95%, and this is 90%. If the p-value is small or smaller than alpha, then we say that the data are statistically significant at level alpha. So in the Girls Rock, Girls R Us example, the one on the back had a very small probability. So if I would have given you an alpha of 0.05 in that one, you would find that your p-value is less than the 0.05. So you would reject your null, and you would say that there is enough evidence to support that the Girls Rock pill increases a couple's chance of having a girl. But we can also say not only are those results significant, they're statistically significant because I've used a statistical process that has shown me that the results are meaningful. So to summarize, you could decide if you're not given a significance level, you reject the null if your p-value is very small. You will fail to reject the null if your p-value is not very small. If you're given a significance level, so an alpha level, you reject the null if your p-value is less than or equal to alpha. You will fail to reject if your p-value is greater than alpha. Just like last chapter with our confidence intervals, you can make a mistake. So if you calculate a 95% confidence interval, 5% of the time we would create an interval that wouldn't capture the mean or capture the true proportion. So the same thing here. I can make a mistake. So my decisions are either to reject the null or fail to reject the null. I could reject the null, but it was actually true. So this is a type 1 error. I reject a true null. If I reject the null and it's actually false, then that's correct. That's a good thing. If I fail to reject the null, but it's actually true, then this is also a good thing. If I fail to reject the null, but it's false, so I don't reject it, but it's false, I really should have, then that's a type 2 error, so I fail to reject a false null. The probability of a type 1 error is just alpha. It's the same as your significance level. And beta is the probability of a type 2 error. I'm not going to talk about how to find beta. Just be aware that you can calculate a probability of a type 2 error, and it's called beta. To decrease your alpha and beta, you'd have to increase your sample size. There's also called something the power of a test. It's related to the type 2 error. It's just the probability 1 minus beta of rejecting a false null hypothesis. So I kind of like to think of it as how good your test is at rejecting a false null, or how good is it at figuring out the right thing to do. And this last sheet, I'm not sure if, I don't think you got the sheet. This one I have some scenarios here where you had to write out the hypotheses and just state what the type 1 and type 2 errors are in words. So in this one, a car dealer claims that at least 24% of its new customers will return to buy their next car. So at least 24% is P is greater than or equal to 0.24. So the null is P is greater than or equal to 0.24. The opposite of that is P is less than 0.24. So if I make a type 1 error, remember I reject a true null. So my type 1 error would be that I reject the proportion of new customers returning to buy is at least 0.24. So I reject this, but really it is that value. Really it is at least 0.24. So I made a mistake because I rejected it. I thought it wasn't that, but really it is. Or I can do the type 2 error, so I fail to reject a false null. So I don't reject that the proportion is really at least 0.24, but really it is less than 0.24. So again, I make another mistake here. So I am not rejecting this, so I still believe this. However, it really is less than this. Both of these mistakes are feasible to make. This one, it has the probability of alpha the same as your significance level. This one is beta. Neither one is necessarily better than the other one. They're just both mistakes that can happen, and just because you're taking a sample, you don't have the whole population. So they're mistakes that can happen, and they each have their own different consequences, and depending on the scenario, a type 1 or a type 2 may be the worst of the two. Here's example 2. I'm going to leave that up for a couple seconds here. You can pause this if you want to look at it. And here's the third example. All right, that is it for this one. I'm off to record more videos.